Let's add a bit more details to this idea of seasonal rainfall change. We looked at the trend of the mean rainfall and said it has reduced by about 10%, or maybe it's recovering and is still part of the multi-decadal variability of the monsoon. Even though that may be the case, as we'll see in the coming years, we can summarize the potential processes by which the monsoon response happens. So here is the monsoon circulation. We've already said it in different ways. We talked about the Tibetan Plateau, the Himalayas, whether they are the barriers or the sensible heating is important for the land-ocean contrast and so on. And we talked about the ocean supplying most of the moisture, even though re-evaporation and recycling is a big part in certain regions, especially the Gangetic Plain. So we had the land-ocean thermal contrast and the monsoonal circulation. The greenhouse effects can weaken or strengthen the circulation. Okay, so here it is shown as a weaker circulation. So ocean is warmer, land is warmer, increased evaporation, and more warming over the ocean has happened. And we said that's potentially because of the pollution and solar dimming over land, which has prevented the land warming as fast as the ocean, or faster as it should with its low heat capacity. And the aerosol effects, we mentioned the rainfall weakening. So we talked about the direct effect, where the scattering and the absorption reduced the solar radiation and the circulation has weakened. All these are points that are debated, as we already discussed. And land use effect is playing a role as well, by either urbanization or deforestation and conversion to agricultural land. And that changes not only the albedo, which could increase the shortwave radiation and cool the land, or it could also be soil moisture feedback, irrigation, urbanization, and sorry if I already mentioned it, and so on. So role of land use change in both the mean rainfall and the circulation changes, as well as the extremes, remains to be fully understood. But we will mention this again when we look at a summary of some of the papers that have looked at the changes in extremes at various time scales. This is another way that has been looked at in terms of the seasonal change at rainfalls aggregated over so-called homogeneous regions. So over time the data has been looked at, and there are countries divided into these sorts of regions with northwest, northeast, peninsular India down here, central east, which includes this massive region from the Himalayan foothills down into the eastern seaboard here, or West Bengal, Odisha, and further into Andhra Pradesh. And we have of course the west central region. And when we average over all these regions, well, that's what we call all India summer monsoon rainfall. And most of the things we have been looking at are all India summer monsoon rainfalls. This study basically looked at the 142-year long time series over these homogeneous regions and the all India regions, and in terms of percentile or quantile changes. So low quantiles, which correspond to dry regions or drought, trends towards drought, and these blue regions where there is trend towards floods. So the figure looks a little bit complicated, but essentially what it has done is shown the long-term average trend in each region. So West Central has a negative trend of about, let's say, 6 or 7%. Northeast has a little bit higher at maybe 8%, and the peninsular India, for example, has increased rainfall about 1 or 2%. Northwest has is mostly a dry region. Of course, this includes the wet regions of Punjab as well, but so it's got an increase of about 1% or so, and overall we said all India rainfall has seen a decrease over this period. And the percentile wise, there is a mixed signal. So there are some regions, this one for example has lost most of the lower quartiles here, lower quantiles, sorry, and that means it has a tendency towards drought. It has seen an increase in the mid quantiles and then a decrease again at the higher quantiles. So this is, remember, seasonal rainfall quantiles. These are not extreme, so one has to be careful, but these are consistent with the changes in extremes that we have looked at, that the large part of central India, for example, has seen an increase in extremes at greater than 100 or 120 or 150 millimeter per day, and a decrease in the lower rain rates of less than 100 millimeter per day, and so on. So the lowest quantiles here have a tendency towards drought here, for example. Not much of a signal overall here, again, other than this multi-decadal kind of signal that we see, despite the overall reduction of a couple of percentiles, percentage trend. Okay, so the main point I would leave with is that there are regions which have tendency towards increased vulnerability to droughts, and there are many regions which have increased tendency towards flooding. And this is looking at droughts or flood events that occurred in the recent past between 2000 and 2013. So you can see these regions have seen droughts, and these regions in stars have seen flood events. So there has to be a consistency in general, but it's not always understood. For example, how is the onset of the monsoon changing? Is it related to global warming, ocean warming, land warming, or something else? How is the withdrawal changing? That determines how the length of the rainy season is changing, and how rainfall is distributed within that. We looked at active break periods. We said overall there is not a significant trend in active periods, but they have become more intense with tendency towards shorter active periods, like 4 to 6 days, with increased intensity of rainfall, whereas the break periods have become less intense but more frequent and potentially longer. So always comes down to intensity, duration, and frequency, even at the intrinsic time scale of active and break periods. So moving now into extreme events again at intraseasonal or sub-seasonal timescales. This message is from Sabir Ali's paper from 2014, which observed that in the past several decades, the MISOs have slowed down. I already mentioned this. So this schematic tries to explain why amplitudes of MISOs changed and why the mechanism of propagation got modulated as well. So both are arguably related to Indian Ocean warming, especially in the west. So that led to increased air-sea interactions, increased moisture convergence, which would determine the amplitude of MISOs, and increased amplitude of MISOs in fact did correspond to increased moisture convergence. They also do a model sensitivity study by prescribing the warming, and argue that these mechanisms are confirmed by the model in terms of changes in propagation speed and amplitude change. So on the propagation change, anomalous moisture convergence over the central tropical Indian Ocean and divergence over the Indian landmass. So that explains the reduced rainfall as well. Modulated regional Hadley circulation. So as we said, when convection is more over the central tropical Indian Ocean, there is less rainfall over India. So there is this local or regional Hadley circulation, upward motion over the oceanic region corresponding to more rain over the water, and downward motion over the Indian landmass. So in an anomalous sense, there is reduced rainfall over the Indian landmass. increased tropospheric temperature over the oceanic region corresponding to latent heating, which is associated with the increased rainfall, and reduced ocean land tropospheric temperature gradient, which would weaken the monsoon circulation. So weakened monsoon winds then lead to reduced easterly shear and moisture gradient across the equator. This is, you can think of it in terms of the thermal gradient and the thermal wind. So land-ocean gradient should also drive a thermal wind shear, which is what this reduced shear and moisture gradient across the equator is. So there is a consistency in the mechanisms of propagation change, even though the northward propagation is now argued to be not just because of the vertical shear, but also because the meridional gradient of zonal winds, the southwesterly winds, produce a barotropic instability, which provides energy for northward propagation. I just threw it in there. If you don't know the details, don't worry about it, or you can go and listen to podcasts in my tropical dynamics course as well. Okay, or there are references that are listed in this paper by Sabir Ali. Modulated, so that modulates the MISO propagation. So northward propagation, monsoon depressions, monsoon trend, active break change, onset, withdrawal, length of rainy season, etc. all have to be dynamically consistent, at least to the extent that similar dynamics are related to all these processes, right? That would make predictions and projections easier as well. Otherwise we'd be in trouble in terms of trying to predict onset, withdrawal separately, length of the rainy season, distribution in time and space of the rain, active break periods, and so on could get very complicated if they're all being driven separately by different dynamics. Okay. This is again from the paper by Dipti Singh, who's the lead author in this paper, looking at time series of wet and dry spell frequencies and intensity over the core monsoon domain. Missing links in the time series are years with no wet or dry spells. Trend lines are estimated using the non-parametric locally estimated scatter plot smoothing regression technique. Shading represents the 90% confidence level, so all the trends here are significant except when you have this p-value which is very high. So till about 0.01 it makes sense, it's a 90% confidence level. Here there is not much of a confidence in the trend when the p-value is so high. Okay, so here 90% of the p-values are obtained from testing the difference in the means of distributions of each variable between 1951 to 1980 and 1981 to 2011. So the latter period is compared to the former period to see if the changes are significant, and they are also done using the non-parametric moving block bootstrap test. Okay, colors indicate the significance level of the p-values, etc. Okay, so frequency in terms of events per year in extreme wet spell characteristics are shown here. Basically the trend is not significant. Extreme dry spell characteristics have a significant trend. So that's frequency in events per year as well. Intensity has a reasonable significance given by P, so that's in millimeters per day. And for active, so here we are talking about extreme wet spell characteristics and extreme dry spell characteristics. Again, there is this decreasing intensity trend in the break periods, which we already mentioned, which should correspond to warming and increased moisture loading and moisture convergence. And remember that even break periods have some monsoon depressions and some rain, so the rainfall in the break period is increasing, so the intensity of the break period is decreasing. whereas the frequency is increasing. Okay, and the frequency of intensity in the extreme wet spells is increasing as well. So there is this consistency in terms of what we said before about the distribution of active and break periods and rainfall within them. So we transitioned from the seasonal rainfall changes and how their propensity for floods and droughts has changed over time, and how that translates to, with various mechanisms, how that translates to active break period intensities and frequencies as well. Now we will go through a table of main results from several papers which have looked at subseasonal extremes, and it's a good exercise because it gives you a good sense of how people have used different data sets, different periods, focused on different regions, and have reached different conclusions. And this is also something that has to be eventually synthesized in terms of the processes over different regions being potentially different, but the fundamental scaling still being consistent with the scaling of the extremes that we saw in terms of vertical motion, precipitation intensity, and Clausius-Clapeyron moisture profile along a moist adiabat. Okay, that's always the main goal.